بسم الله الرحمن الرحيم، والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. السلام عليكم everyone. Hope you're all doing good. Today, inshallah, is the last lecture of this mini course. We'll start as usual with the recap of the whole of what we discussed so far, and also what we're going to be discussing today in this final lecture. Excuse me, my voice today is completely gone, so I won't be able to make it louder. Today, inshallah, we're going to be emphasizing again this idea of passivity and why is it important. And then we're going to be looking at why when we have a standard impedance control, it's passive, and why when we just try to have variable impedance or variable stiffness, we lose this passivity, and what are the consequences of that. Okay. And then I'm going to be introducing to you this new way of looking at dynamical systems or at robot control, which is coined as energy-aware control. And we're going to be looking at, so this third part will be just in general, what is energy-aware control, what are the ideas, and then I'm going to show you how can we do impedance control in this new framework with this energy awareness. And again, I'll show you, inshallah, some cool videos in the end. As a recap of what we discussed, we're doing everything in the geometric Port-Hamiltonian framework, which has the roots, or it combines three different ways of thinking. The first one is port-based modeling, where you look at subsystems connected together using ports, and each port is a pair of effort and flow variables that in the end, when you pair them together, depending on where they live, so you pair them together, you get something which is in powers. The second one is geometric mechanics, which is this way of looking at dynamical systems independent of the coordinates, how we write them down. So we try to always look at what is the underlying structure, mathematical structure that where this lives, where these signals live, or this time evolution lives. And usually we have some sort of manifold where this where the state lives. In general, we call this the state space. In classical treatments, you just say X belongs in Rn. It's just a vector of X1 and X2 and X3 and X4. In general, this is hardly the case. And this is not, again, this is not mathematical. So even a lot of interesting robotic systems have this structure. So it's not just some way that mathematicians think, okay, why don't we look at a general thing that's not Rn? It's really coming from practice, from practical purposes. And the last part is the systems and control theory, which you all should be aware of. And when you combine all of these three together, you start to look at systems differently. That's the first thing. So you don't look at it no longer as x dot is equal to f of x, where f is everything. You start to give it some structure. And because you have this structure, why don't you use it for control? That's the whole idea. So because I have the structure, can I exploit it? Can I use it for control so that I can define either, you can either take the old controllers and think about them differently, which means that you can extend them in different ways because you're looking at them differently, or you can think of new controllers that no one ever thought about. And I'll tell you two keywords if you want to dive deeper to this Port-Hamiltonian control, inshallah, today. And in the end, you start to have in one system, you start to talk about subsystems of this big system, and you're going to be finding in the end, you can always describe any subsystem inside of your bigger system as something that either stores energy, dissipates energy, or supplies energy, and everything else is just energy routing. Okay? It's just an interconnection structure that combines all of these, that connects all of these together. And we talked about this way of representing systems, which is using ports and using Dirac structures. So Dirac structures is this, this building block that combines different parts together, that, attaches like the glue of, and it's at the heart of what Port-Hamiltonian systems is. For a flying end-effector, which is just a fully actuated hexarotor with multiple propellers that in the end you can generate a collective wrench on the drone. We say that this control wrench, I can precisely say what it is with the propeller. So we do not talk about this problem, which is if I have a control wrench, how can I transform it into individual propeller speeds or propeller forces? This is something called the control allocation problem, out of the scope of here. But in general, what we do here at this stage is that we say, I have full control of the wrench. I can provide any one of the six degrees of freedom, and I can apply it directly to this model. So in the end, we just have the whole drone is one rigid body flying. This is the equation of motion of a rigid body. Evolution with the first one, kinematics, finding the rate of change of the pose of the robot. And the second one, where the pose of the robot is simply the pose of some frame attached to the center of mass, rigidly to the body. And the dynamic equation is simply the rate of change of angle of generalized momentum, which is angular and linear momentum, is equal to everything else. We have the gyroscopic and gyroscopic torques, Coriolis forces, all of them combined in one term. We have the gravity wrench, we have the control wrench, and we have the interaction wrench. The interaction wrench comes from the fact that this drone is not going to fly from point A to point B and that's it. It's going to be doing stuff. It's going to be pushing on a wall, opening a valve, trying to insert a key or something. So it's doing stuff. So there's always this reaction wrench from the environment on the drone itself. The equations of motion can be written in the Port-Hamiltonian framework. It looks like this. We discussed it last time. And you can also the first thing that you can write this equation is that you need to think about what is the underlying energy. So in the first two equations, you see there is no energy. It's just, I have two states, two variables, and I have an evolution in terms of these variables. So the only two variables that I have are h and p. So h here is the pose and p is the momentum. And I have here a twist, which is simply the inertia inverse of the inertia multiplied by p. So this is also a function of p. This is h, this is a function of p. This is p, and I have external wrenches, And even the wrench itself, it's just a constant, But in general, it also depends on the rotation part. Okay, in general, it depends on how you rotate. So we do have a rotation matrix here. So this is a function of h. So you see, everything is in just a function of h and p. The starting point is that you need to think about, if you want to write any system in a Port-Hamiltonian form, you say that what is the underlying energy that they have? And this is a mechanical system, so it must have kinetic energy and gravity and potential energy. Here, there are no stiffnesses inside of the drone itself, so it just has gravitational potential energy. If you have a manipulator, it still has kinetic energy and potential energy. If you have a soft robot, you're going to have also extra stiffness. I have compliance of the robot itself. You still have potential energy, okay, elastic potential energy. And this is how we can write the equations down. Just as a side, did anyone manage to transform this equation to this equation at home? Yeah.
Where I was facing the issue.
Yep.
Some of my colleagues is this final taking the Hamiltonian.
Yes.
The differentiation with respect to it.
Yep.
Here we don't really have H here, so consequently the derivative should be with respect to the pi that's there, right?
Yes.
But then how exactly it's done? Because when we do it directly, what we get is mg transpose.
That's right. Yes, exactly.
But then how exactly we convert mg transpose back such that
you get a range?
Yeah, it is the range.
Yeah.
But then
no, it's not the range. Mg transpose is
the force,
only the force part. Yeah, exactly. It's only the force part of the range. Yes. Yeah. So what you need to do is that you're going to be having some sort of way that will take this force and make it into a range. That's it.
But the whole idea of this map here is we're taking it from the dual space, the cotangent space.
Yeah, exactly.
Exactly.
Yes.
Star.
Yeah.
But then this is not in that format. That's the point.
That's right. Exactly. Absolutely. So all of the remaining parts are very easy. Well, this is the only difficult part. Okay. But what you need to know is that this is so the first part, which is the minus of the chi invert the chi transpose, which is a function of h, and it eats the gradient of this Hamiltonian function with respect to the pose of the rope. So this term, in the end, you should get is equivalent to the gravity wrench. Okay, all of these details are skipped. In the next couple of slides, you're going to be seeing that we have something very similar, where if the gravity, the wrench is related to the gradient of the gravitational potential energy with respect to h. You can also have the wrench due to spring is equal to the gradient of some elastic potential energy with respect to h again, and the chi map will appear again. I did not discuss all of the details about this because this will require some time. Okay, but if you want, I can show you how to do it. Okay, but in the end, the gravity wrench, you can write it. I can show you some stuff if you want. You can write it like this. So for now, you just need to know that this is the gravity wrench. Okay, just like when we had earlier, when we had like the mass spring, the mass damper system with gravity. When we had the mass damper system and there was gravity inside. So the minus mg that appeared in the equation, remember this force, we wrote it as the gradient of the function, the gravitational potential energy function with respect to the sign. So this is the same term. I just want you to know the analogy without the technical details yet. Okay, so the technical details are aside. In the end, these are equivalent. Okay? Any more questions? Okay. The Port-Hamiltonian model of the flying end effector in the end looks like this, which means we have something that is a skew-symmetric matrix. It's not 100% matrix, you know. Don't think so, because now we're working with geometric stuff. This is not a matrix that you multiply, because the chi itself is not like a 6x6 or a 4x4 or anything. It's just a map. So this is a matrix operator. You can write it as an operator. It will eat these two terms and in the end give you something that can relate to h dot and the p dot, and the rest are it's straightforward to see. The energy analysis, so what's the power balance do I have here inside of the system? So we talked about, we introduced this energy because we just, you know, we made it explicit in the equations. It was always there. It was, you know, you did not consider it before. So when we explicitize this, we have that the rate of change of this energy you can show in the end is equal to the power supplied by the controller and power supplied by the environment. Okay, all of the steps in between, you can just eyeball it. You don't need to do any math, simply because everything related to the J, what happens to it? Just disappears, okay? Because of the skew-symmetric property of this J operator. And you can rewrite these equations into something which we call the Dirac structure form. So there is an underlying Dirac structure, which is this 4x4, you know, matrix operator again, that will map effort variables on the side or map some inputs that could be effort or flow of some port here. You see, for example, the gradient of H with respect to, so the gradient of the energy with respect to H and the gradient of the energy with respect to P. These are two effort variables of this port. And the wrench, which is due to control and is due to interaction, are the two efforts of these two ports. So in the end, I have 4 efforts here, and I have the corresponding 4 flows there. And if you do effort and flow, effort and flow, effort and flow pairing, depending, of course, on where they live, these are 6 numbers and these are 6 numbers. So you just take the inner product, 6 numbers and 6 numbers, inner product. Here, the gradient of the energy with respect to the momentum is also 6 numbers. You just multiply by P dot. The only one is left is this part, which is again related to the same technical difficulty that you need to take into account, the SA3 structure. But in the end, you just have that the total, okay, all of these ports, they sum to 0, which means is that, so these two paired together are the rate of change of the energy. So these two rated together are the power supplied by the control, and these two paired together are the power supplied by the environment, okay? No matter how complicated the system is, it simply boils down to this simple fact, okay? So all of the nonlinearity, all of the technical details, they just disappeared in the energy analysis. Okay? Very important to note that. And then we discussed last time impedance control. We said impedance control, the whole idea, which was introduced by Neville Hogan, is that not to think about controlling force or equivalently wrench alone and position, okay, alone or pose alone. You start to think of defining the behavior, the desired behavior that you want the system to behave with respect to the interaction port. So the key is in shaping the robot's dynamic behavior, not just controlling one of these two variables. Don't get me wrong. This doesn't mean we're going to be controlling the pose and the wrench in the end, but we're going to be controlling them indirectly by saying what the desired behavior should be, not the other way around. We looked at the mass damper system just as a prototypical example. We had the equations of motion and the impedance control law. In this simple case would be first to cancel the gravity, add some proportional term and some derivative term, but you can also think about this proportional term and the derivative term as a stiffness and as a damping force, which in the end, when you plug in this control law in the original equations, you can rewrite it into this one equation that corresponds to, with respect to F internal and V, or the psi dot, we just have a mass spring damper behavior. So the environment, are you aware of this idea in electrical circuits of Norton's equivalents? Have you heard about it before? Norton's equivalent. When you have an equivalent circuit, equivalent resistance, and equivalent circuit with respect to some voltage and current. Does this ring a bell now with what we're doing? It's exactly the same. The equivalent behavior of all of that you had in circuits, for example, all of the nasty circuits, all of them on the inside of the of your circuit, which is resistors and capacitors and parallel and series, and you have inductors and everything. They can be linear, they can be nonlinear, are equivalent in the end with respect to the input and output, with respect to the load, as an equivalent circuit, as an equivalent impedance. It's exactly the same idea. Okay? Exactly the same idea. With respect to the interaction port, okay, this effort and flow variables, the robot only sees a mechanical impedance. That's it. And it's defined by this equation. So this is the idea that you design a controller such that the closed loop behavior would act as something that you want to desire. You want the robot, you want the interaction to feel. And it works both ways. So there are two fields that rely heavily on this idea. The first one is robot control. Okay, so interaction control of a robot, which is that you want to have a robot, you want to do, you have a manipulator, okay? You wanted to tie a screw, you wanted to open a valve, it's doing something. So with respect to the valve, you want the valve to see the robot and its controller acting as a mass and a spring and a damper. Of course, it has to be in 6D, right? So this wrench and a twist, so it's more complicated, but in the end, it's just equivalent to a mass and a spring and a damper system. Another field that relies heavily on that is haptics. So haptic devices. So when you have a haptic device and you have a user that's using this haptic device and is trying to render some sort of simulation or some sort of dynamics that's happening maybe on the other side of the world through the internet connection or in the simulation environment. So the haptic device is nothing else than a robot. So it's a robot that you're controlling now as a human, and you want it to act as if it's a virtual spring or a virtual damper or something like this. So these are two very related fields, okay, that rely on this simple principle. Yes.
It always in the case of it's safe to say that when we are always able to rewrite the equations after adding our controller in such a way that the interaction range of force is equal to some mass spring damper system.
Yeah.
Then we have
you always have a behavior. That's the thing. Even if you have something here that MPC or reinforcement learning, you can always think of what does the environment see. Okay. Usually you have signal processing, you have optimization equations, and you just you're doing signal processing. So this is one way of doing control. But the way we're doing control here in the Port-Hamiltonian framework is that the controller is not a signal processor. Is another system with dynamics, and now I can design these dynamics, just like when you say, instead of deriving the control law just from some optimization loop, I have the control law that is equivalent to some virtual physics. That's the idea. So I'm adding physics to the system. So this is a different way. I'm not saying it's the best one. It's just it's good for many problems. Okay, I'm not saying this is the way to do all types of control. It's well suited for haptics, and it's well suited when you have a robot that's doing interaction. Okay, and of course you can always argue that that's not the case. Okay, especially now with the trend of doing data-driven control and doing model-free control and doing just control by trial and error in a simulation or with reinforcement learning. So I don't know whether this will become obsolete in 5 or 10 years or not, but it's still one way of doing control. Okay, so that's my philosophy. It's not universal. When you have an SE3, this flying End-Effector, the energy of the controller, we said, the energy, sorry, of the system is the kinetic and potential. We have the Port-Hamiltonian dynamics given by this equation. The impedance controller, you can think of it now as another system with dynamics. And we represented it last time, as you see here in this graph, in this bond graph. It has a Dirac structure of its own, so something in the middle that will attach multiple things. Let me go back a slide first. So just to remind you that this was the bond graph of the flying end-effector, and it had the Dirac structure, and it had two interaction ports, one with the environment. We don't know what it is. We don't know what's on the other side. We don't know how to model it. We don't know what we're going to be interacting with. So we just leave it open. And the robot itself had kinetic and potential energy. It stores them. There's no dissipation inside of the robot itself. We're not considering any damping of, for example, of aerodynamics and all of that stuff. We neglect it. And the controller is simply, in the end, no matter what it has inside of it, it is something that, if you want to think of it as connected to the robot, it will apply to the robot the wrench and get from it the twist. So what you're going to be seeing in the next slide is more blocks inside of the controller. Okay, so we're going to be zooming in inside of this impedance controller, and you're going to be seeing it has multiple blocks. In the end, it has this port, which is the power supply to the air robot. So this one, you connect it to the other one, and you get a new Port-Hamiltonian system. And this is the main, the strongest property of Port-Hamiltonian theory, is that when you have a Port-Hamiltonian model and you connect it to another Port-Hamiltonian model through some, through a particular way of connection, like, for example, just taking a port and equating it to a port, or through another Dirac structure, the resulting, overall system is another Port-Hamiltonian, is a third Port-Hamiltonian system. This is very powerful, okay? So the bottom line is that you can just learn about Port-Hamiltonian theory and you can just expand, It's not like that after a while you start to have something that's not written in Port-Hamiltonian form. You're always going to have this, provided that you do the interconnection properly. So the impedance controller now, which as an idea is simply just a mass and a spring and also stiffness, gravity compensation, can be represented as a virtual spring. You have a storage of potential energy, a virtual damper, which is a resistive element or something that dissipates the energy, and you have another potential function that corresponds to the minus of the gravity. So if the drone has positive gravitational potential energy, we want the controller to have negative gravitational potential energy so that they cancel out each other. That's the idea. So the equation of the damping is simply some matrix multiplied by the twist. The energy function, which is the energy stored in the controller, it has two parts, something related to the gravity minus the gravity. So it's minus mgh, you see. And we have something that corresponds to a spring. When I say a spring, what comes to your mind? What's the equation that comes to your mind? Half kx squared. If x was a vector, how do you write it? Half x transpose kx, right? This x, where does it live? R3. So you're only talking about a linear spring. Can you do the same for a rotational spring? So if I give you this point and this point, what does a linear spring do? It just, makes them oscillate like this. If you have two frames, can you connect between them a spring that will make this frame, align with that frame? Assume I have two right hands, Okay. So can you have a rotational spring? In principle, yes. What is the equation of it? It has this form without any technical details. You should have seen this equation before, okay, in the geometric control course. So this is the potential function of a spring on R3, on SO3. And this part that you see on the right-hand side is simply half, almost, it's half psi transpose K psi, which is equivalent to half X transpose KX, okay? There's just a small technical detail without going into without explaining why, is that when you have a spring on SE3 and you have this half, so this is the rotational part and all of this is the translational part. The translational part, you don't want it, it's not as easy as, just saying half X transpose KX, because you have rotations, right? So a spring, it acts on the right, so on the first terminal and the second terminal in the same force. If you try to write half X transpose KX for a spring for a linear spring that has something with rotations, you're gonna find weird stuff. And a lot of people studied this in the past, and they found out that a good symmetric spring on SE3 needs to split the half KX squared part into something that is written like this and something that's written like that. So if you want more details, you can look it up. But for now, this potential energy is simply a rotational spring and a translational spring. Can you derive it? Can you make it into a gradient and then convert it into a wrench? Yes, of course. How can you do that? Using the chi map. Okay. So the same technical details that I skipped by writing the wrench, the gravitational potential energy as a wrench, is exactly the same technical details, how you can transform this potential function into a wrench due to spring. Okay, so it's skipped. Yes. Absolutely. Yes. Translation. This is translation. This is exactly equivalent to X transpose KX. And this is something very much like it. You know, it's X transpose and X, and there's something in between that has a K that's multiplied before and after by rotation matrices. So you can think of it that this is a spring, and this is also the other part of, you know, it's the half we divided into 1/4 and 1/4. So half KX squared we divided into 1/4 and 1/4. And here we took the K represented in one frame, and here we took the K represented in the other frame. That's why we have this rotation matrices. This is just in a nutshell what it's doing. The G, yes. So here K, KT, and so this is called the stiffness matrices, just like what you're used to on R3. The G itself is called the co-stiffness matrix. And you can derive it, you can write it in terms of another KO, you know, K for orientation. And what you can also have is that you can have coupling. So you can also have an extra term that will couple rotation and translation. So in general, a spring between two frames, you can, and the wrench it generates, you can think of it as the sum of a linear part, a rotational part, and also a coupling part. Okay, so this is the most general way that you can write a spring. This is the most general way that you can write a linear spring. And now you can look at this and you say, is this linear equation? Of course not. So this is a linear spring, but because of the nonlinearity of SE3 itself, it looks very complicated. Okay? So that's the reason. So there are two types of nonlinearity. You can have nonlinearity in the space itself, which is SE3 is by naturally, okay, it's naturally nonlinear. So this is a linear spring that infinitesimally is linear, but when we write it in terms of on SE3, it becomes this nonlinear form. Okay, and I can also add nonlinearity on this nonlinearity of the space. So this is a linear spring on SE3, and this is why it looks just nasty.
Minus half the trace of the multiplication of the rotation matrices, which the torque is related to the proportional part.
It's exactly the same term.
This is good same thing.
Exactly. What's different here is that, so earlier, for example, in the course, I introduced it as not minus trace, but only as trace. There was no minus. It was only as the trace with the matrix multiplied by I minus R. And the R itself was written as R transpose R. If you remember, RD transpose multiplied by the R base. And this R that you're seeing here is the relative orientation. It's like the error. It's the relative rotation between the CS frame and the D frame. The CS frame here is something that we added just, you know, for having the same controller to do two things. So here we're doing impedance controller if you put the CS frame at the E frame. So in other words, if you attach the spring, where is it? If you attach the spring to the tip of the robot, then you're doing interaction control. But at the same time, you can also attach the spring at the B frame. In this case, you want the robot base itself to go to this desired frame. So with the same controller, you can do both motion control and interaction control. Okay, so that's why we introduced this CS frame, and you're going to find everything is written in CS.
Assuming linear spring mixed problem.
Assuming a linear spring in, I think you mean in the environment. Yeah, here we're talking about the controller. So if you're doing, so if you don't have this tool to deal with how can I analyze a system that has an open port, then what you need to do standard Lyapunov analysis to conclude, for example, stability, you need to say what the environment is. So why not just assume it's a spring or a damper and just with some linearity and that's it. So that's the thing that's wrong. Here, when we go do the analysis next, inshallah, you'll be seeing that it's an open port. We treat it as open. We're not going to make an assumption about what the environment looks like, but we're just going to make an assumption about the behavior of the environment, as I'm going to look next. Yes?
So that we can also have a coupling term that couples the rotation and the position. This third term, isn't a term that is actually dealing with the rotation, the rotational effect of the translation?
That's right. This is a term that already has coupling between the rotation and translation. That's absolutely correct. But in the end, it will act infinitesimally as a linear spring that corresponds to the translational part. And this one will infinitesimally act as a linear spring with respect to the infinitesimal rotations that you have. You can also have, when I have an error, I rotate. This is the behavior that you can have. Something very popular with that is actually a peg in a hole problem. For example, some people found that if I want to do a peg in a hole, let's say I take, for example, peg in a hole is a typical problem where you have a hole and you have like some rod and you want to put this rod with a robot inside of this hole. And the hole can be as small as possible, it can be very small. And then you can take this peg and let's say that you put it till this point, just hit the tip of the hole, okay? Something very natural that you can do is that once you have, this behavior, what you can do next is that I can rotate, then I go down easily. So you see, if I have an error in position, I can rotate and not go down. You don't want to go down actually, because if the spring, so if you want to press on this wall, okay, this is the wall, okay, at this point, and the spring, you see, if I have a linear spring, what's the behavior you expect? I'm going to keep pushing. If you make the spring bigger and bigger, I have an error in the position, and I keep pushing. I keep producing a force. But the best behavior is if you have an error position, produce a torque so that you can do like this. So this is a typical scenario where you might want to have this coupling term. Of course, when you're doing something very complicated, you don't think about it. So for example, if I give you a PCB and I tell you to solder all of the small parts of it, you're doing all of this interaction. You're not thinking about, I'm going to change my impedance and so on. You're doing it without thinking. But you are actually changing the impedance of your arm. You're actually, stiffening your hand. You're making it sometimes soft, sometimes hard, and so you're changing your impedance. Okay. If you're walking in the dark, okay, and you close your eyes, you don't have uncertainty. You're walking like this. You're walking very small, and you have your hands, your muscles are very soft. But if I open my eyes, and I'm holding like a tray, and I stiffen my hand, and I walk very confidently, I'm very stiff. I have high compliance. You do it without thinking. And a lot of people, actually Neville Hogan himself had a lot of work. He's very interested in biomechanics also, right? So he's using all of this to do rehabilitation robotics and try to understand now how can we, enhance the impedance, or how can we, when we're dealing with a human subject, how can we deal with his impedance? So he had a lot of nice work on this, impedance matching and stuff like this. Okay. Yes. Yeah. Where are the 6 numbers? The H itself. Linear algebra. Sorry? The Lie algebra. That's exactly what happens here. So when I say that this equation is a linear spring infinitesimally, I actually mean in the Lie algebra. That's absolutely correct. And so if you define in the algebra a linear spring infinitesimally, and you exponentiate it using the exponential map to the group, you get this function. That's exactly how you get it.
But if we think in algebra, we have something very linear, just only one single k. Is this possible?
That's exactly what you have. This K that you're talking about is a 6 by 6 matrix that has in the top left corner KT, this 3 by 3 matrix, and in the lower right corner KO, not GO, the KO, the stiffness corresponding to this co-stiffness, and you have in the diagonal, in the off-diagonal terms, you have 0. If you add there some K coupling, you get here an extra term. Exactly the same. Okay.
So basically, it's a rewriting of the same expression, but then in that particular version.
Yeah.
To make it more.
It's equivalent. It's equivalent, actually. And in the end, having it as an energy is just an extra thing. You remember I said that you need to think about the energy that you can write the Port-Hamiltonian system. But in the end, the equation, you just need a wrench. You just need 6 numbers that correspond to the spring force. If you look in the paper, you're going to find the expression of the spring. It's very nasty. Okay, look very scary. It's not something that you're used to. But in the end, it's equivalent to the gradient of this potential function with respect to the pose. Okay, so all of these technicalities is just because we have an SE3 manifold underlying. So this is what I just said, that in the end, we have a virtual spring. Okay, we have a wrench due to a spring. We have a wrench due to damping, and we have a wrench due to gravity compensation. And they're all connected. All of these twists and wrenches from the output and the input of this controller are connected through this Dirac structure. It's another Dirac structure, but now this is a Dirac structure of the impedance controller itself. And you can look at it at your own pace. You're going to find that these actually equations are much more familiar if you just write them down. We have a lot of zeros here, just so that we can write it as a big map. But the first equation is simply 2 twists, okay, summed together. One is a plus and one is a minus. So actually, we're taking like the relative twist between 2 frames. This is exactly the first term. The last equation is what you see here in this equation. So the last equation the last row in this Dirac structure is nothing else than this equation, which is a damper represented in the B frame, a gravity wrench represented in the B frame, and a spring represented in the CS frame. And then depending on where the CS frame is, I must transform this wrench back from the CS frame to the B frame. This is exactly what the equation says. If you're doing motion control, this adjoint is simply identity, because the B frame and the CS frame are the same. If you're doing interaction control, you just need to take into account, this extra transformation from the B frame to the E frame. So this is the controller. So this is in the impedance controller. Without all of the technical details about SA3, it's simply a spring, a damper, and a gravity compensation, exactly the same like when we had the linear case, the mass damper case. You can show that this controller is passive, which means you have guaranteed contact stability, as we discussed last time, and we also have robustness, as I showed you in the experiments last time. Now let's emphasize this idea of passivity. Okay, this is what we discussed last time, because this is part of the recap, but I want to emphasize it more. In general, for any nonlinear affine system, a nonlinear affine control system that has state and has an input and an output written in the standard form you're used to, a system is passive if you can find any, and this is the general case, if you can find any non-negative state-dependent storage function, V of X, such that you have this property. Okay. Equivalently, this is equivalent if you have certain, if you have certain differentiability requirements on the V, you can write it as V dot is less than or equal Y transpose U. Okay. In the time domain. So why passivity is important? Because it implies stability. If I have a system that's passive and I don't apply any U, which just means I'm looking at the autonomous system without any input, this means that I have a function that says that it's going to go into 0, forever. It's going to be going until, it just dissipates. It's not energy, by the way. We're not talking about energy. It can be any function. And this V, usually if you have the autonomous system, you don't have any inputs and outputs, you use this as the Lyapunov function, you just conclude stability of the system. Not asymptotic. Asymptotic is an extra stronger condition, but at least stability is what you can get from here. In the Port-Hamiltonian formulation, this is completely natural. We already have the equations written with the energy explicit. We have a very good candidate for this V function, which is just the energy of the system that we already have explicitly. And as I showed you last time, it's straightforward that the pairing between the effort and the flow variables that make up the H, or the H dot in this case, is simply equal to a term that's always negative semi-definite, sorry, and you have this term that corresponds to the power supply. So naturally, just from the Port-Hamiltonian system, you can immediately, without even writing this one line, okay? The J disappears in this analysis. The R is always going to be causing damping. The G always disappears because you have a G and G transpose. So in the end, I always get H dot is related to Y and U directly, just one line. You don't even need to write this one line. Okay? And equivalently, because we have this, differential inequality, can also extend it to this integral inequality, and we have the passivity property. Yes.
Both of them are equivalent to the
Yes. The condition is on the differentiability of the H. In the previous theorem, we said that if you can find any V here, so I said we can find any V that satisfies this. But this V can sometimes be non-differentiable. It can have, like a discontinuity. It's a function. So you cannot write it in the differential form. That's the idea. So they are equivalent if you have V to be differential, just in general. Let's see.
Regarding the line of the Lyapunov function.
Yeah.
Even when reading the paper, I didn't understand what is under the weak conditions that qualify as switch function.
Because there are extra stuff that we need to have a Lyapunov function. For example, it has to be positive it has to be positive definite, and it has to be zero equal at the zero part. But you can always play around with this, if it's negative or if it's non-zero at the zero, you can always add a constant, to make it zero. If it's if this function also so if here the extra condition that you also need to have is that the V should be positive definite. If it qualifies as a Lyapunov function, but here not. V can be also non-positive. Okay, sorry, it's non-negative is different than positive definite. That's the difference. Okay, so here we require V of X to be positive definite, which is stronger than this condition, which is just non-negative. Okay, these are two technical, details. Okay, as functions. One, yes. Once they're written in the Port-Hamiltonian form and use the H as the storage function, then J disappears, R makes this inequality, and you're only left with the U and the Y. Exactly. So, very good question. When we talk about Port-Hamiltonian systems and we talk about energy and stuff, usually what we're thinking about are physical systems. Okay, so the Port-Hamiltonian is very strong when you're dealing with physical systems. The general one that you saw earlier, the X dot is equal to F of X, you can have any system that you made up with your mind, It doesn't need to be physical at all. So this is definitely more general, but more than what we need, That's the idea. If you're dealing with physical systems, if you're only, if you're working always in physics, so all of the dynamic systems that you have will always come from this energy. There will always be energy there. If you're working with mathematical systems, you just make up some mathematical system and you say, okay, I have this. I'm not saying it's not useful. It will have its applications. Okay. For example, let's say that you want to model the dynamics of how COVID spreads, how a pandemic spreads. You can write it as an equation. And it doesn't have to come from an energy, it doesn't have to come from, from physical dynamics. It's just a differential equation on its own. You can study it, and this is why this is more general. So the same, so passivity, and there's also a more broader term called dissipativity. These are when you have this generic form of a dynamic equation, of a nonlinear dynamic equation. Port-Hamiltonian system says that is a much limiting, okay? But exactly what we need for our applications when we're dealing with physical systems or when we're dealing with robotic systems, which are just mechanical systems, okay? They can generate. So here the H dot is less than or equal this term. If you want to, so this is passive with respect to this port. But what happens with this port on the other side, I don't know. So this says that this one alone is passive with respect to the port. If on the other side, Y transpose and U are coupled together with some other dynamics that are also passive, then you have the one passive system connected to another passive system. What's the result? A passive overall system, and then you can conclude stability. And this is why the passivity is important, because where is it? No. So the passivity is important because if you have a system that's passive with respect to this input-output port, if the dynamics of the input-output port are passive, this is the only assumption you need to make. Then when I connect this H dot with this, so when I connect this system with the one that I don't know about, but I just make an assumption that it's passive, I have guaranteed stability when both of them are connected. In the case of a robot, it means that this X dot can correspond, for example, to the open loop system and also can correspond to the closed loop system, okay? So assume that this corresponds to the closed loop system, which means that J of X and R of X and all of this includes the original dynamics and also the controller dynamics. And the U and the Y are some extra port I'm going to be connecting into the outside, which in our example, for example, was the interaction port. So because if I have a closed loop system that's passive with respect to the input-output port, this means that if I have a robot, a controlled robot that's connecting, or in other words, it's interacting with a passive environment, I have conclusion that the contact stability, I have conclusion that the closed loop system, when it's in contact, it's stable. It's not going to be blowing up. This is very important. Okay. Yes, Pansy. This is very general. We're not talking about anything. This Hamiltonian. In this example, written like this, if you go back to the previous slide, we assume that X lives in Rn, just to write it like this.
H of X times H of X zero, like the last equation, because it's not a vector space.
Very good point. Okay, I see your point. The H itself is a map from where to where? From a state space in general, so any manifold in general, to R. So what is H of X? A scalar, energy. So energy at time t, so this equation you can read it as follows. The energy at now minus the energy I started with is always decreasing. Okay. Or it's always less than the energy supplied from the outside. And if I don't have energy supplied from the outside, this is less than zero, which means I'm always decreasing. So the energy I have inside of the system that's corresponding to this equation 1, 4, and 5 is always decreasing if I don't supply energy from the outside. What is the type of system? What are the type of modules that only have energy going, not increasing? Okay. By the way, this is less than or equal 0. So it can be sometimes 0, and it can sometimes be negative. Sometimes can be increasing. So it's non-increasing. This is how you call it. You don't say it's decreasing. Because decreasing means it's always, at every time instance is less from the before, but you say it's non-increasing. Non-increasing means that it can either go down or stay as is. Go down means you have a damping. Stay as is means you have stiffness, or in general any C element. Any something that only stores energy. Okay. Inertia stores energy. Stiffness stores energy. Potential gravity stores energy. Right. Damping or friction, they always dissipate energy, and so on and so forth. Which is corresponding to the bond graph we saw earlier. These are the R, the C elements. Okay. So in the Port-Hamiltonian form, okay, so this is the standard, okay, the form I showed you earlier. And if you look at it from a block diagram, you just write it like this. But you can always, as I showed you, you can rearrange it into this underlying Dirac structure, and you have this equivalence, okay, between these two equations. These are exactly the same. And the underlying Dirac structure, you see, it just has the J and the G of X, okay, that correspond here to all of the terms that we have inside. There was the question last time that what about the R? The R doesn't belong to the Dirac structure, and the Hamiltonian doesn't belong to the Dirac structure. They're always outside. You see, the Hamiltonian here is part of the storage, and the R is part of the dissipation. So you have this separation between storage, between dissipation of energy, between energy routing, and you have between energy supply. Yes.
The YR,
Yes, these are extra. We introduce extra variables that correspond to the UR. So here in the equation, the R is in between. Okay. So you can always add some extra, details. You can add an extra port that you can call the U. You can add a new U, which is the R, and this is the one that's connected here. So these are exactly the same equations. Okay? I just wrote them like this so that you can really see the R outside of the J of the Dirac structure. Because if you put this inside, you don't have here the equality, okay? Because of this dissipation. This is why we need to take it out. This one, so in this original equation, there was only U and Y. We did not have any R part because it was already this R multiplied by this. So minus R multiplied by this, let's call all of this UR. Okay, so let me remove all of this part. And I'm going to just add plus G of X multiplied by UR. So, just minus UR here, you see? So I'm going to call R of X multiplied by the gradient. I'm going to be calling it UR, and I'm going to be taking outside. And this UR is equal to, you see, R of X multiplied by YR. What is the YR? The YR is simply the gradient of X. You see what we did? Just a small manipulation. We added this extra variable, okay, so that you can write this equation like this. And this is, I think, related to a good question that was asked by Muhammad before, that is it always possible, to start with a X dot is equal to F of X and try to manipulate the parts so that I can write in the Port-Hamiltonian? Yes, in principle. But you need to know where you're going, That's the idea. So if you know all of this, detail that you need to write it like this, you can always do this extra. But you see, it's completely natural that if you start here with this form, it's very easy to go to this one. And it's also very easy to go to the X dot equal to F of X. But sometimes the reverse is not that easy, okay? Especially when you have terms that cancel out and, you need to introduce a lot of intermediate variables like this and so on. Okay? Sorry? It doesn't have. We remove from it the R. The R of X, we removed it outside. Okay? That's exactly what we did here. Okay, so this is a little bit of, so C corresponds to a storage element. Okay, so this is the bond graph terminology. C corresponds to a storage, and we write it 2 dots, and H of X means this is a storage, and this is the energy function. Here, this is called a modulated resistor, or a modulated resistance element. It's modulated because the R is a function of X. If it was only just R, as a constant, sometimes in the bond graph, they call it just an R element. So modulated means it's a function of X. That's the only reason. Okay. MTF is a modulated transformer. Okay. The transformer is a type of Dirac structure that has an input and an output port. It relates the effort to the effort and the flow to the flow. Or in general, it can also relate the effort to the flow and the flow to the effort. So the input flow to the output effort and the input effort to the output flow. And sometimes they call it in the bond graph the gyrator. All of these are technical details. In the end, it's just a Dirac structure. Okay? I usually prefer to always have, just Dirac structures written like this. Yes, ma'am.
I think this RX will help us in the interconnection between the subsystems, where we have only U and Y, but we don't deal with the UR and UY. That could be from other system that is connected.
At this stage, no. It's already, think of it as a port. It's already terminated, I don't have anything else I can connect here. It's already like the U and the UR and the YR are already plugged into a resistance, to this relation. This is the only open port that I can connect to other stuff. So this is the one I use for interconnection. This one is already dissipating energy. Okay. So passivity-based control. So there's a whole field of control called passivity-based control. It's a set of techniques, a bunch of techniques where you think about designing a controller such that the closed loop system is passive. Okay, so this is the aim of how do we design this control. In the Port-Hamiltonian control, in the Port-Hamiltonian formulation, it's completely natural, as I said. So passivity is natural. So also passivity-based control is also natural. And the whole idea, and this is the property I told you earlier, that when you have two Port-Hamiltonian systems connected through this open port, which is the U and the Y, the resulting Port-Hamiltonian system, the resulting system is also in Port-Hamiltonian form. Okay, so when we're designing a Port-Hamiltonian controller, usually the aim is that the closed loop system is another Port-Hamiltonian system. And there are two famous techniques, okay, that are well established in this way. One of them is called the energy balancing, PBC, the energy balancing passivity-based control technique. And the other one is called the interconnection damping assignment passivity-based control technique. So IDA PBC and EB PBC. The idea is very simple in both cases. In the first one, in the energy balancing technique, you say that if this is the original system and I have U and Y, which correspond to my controller, I want to design the U and the Y such that the X, the new X, which is the closed loop, okay, X, will have the same J, different R, and a different H. So same J, different R, different H, and same G. This is exactly what the energy balancing technique means. Okay. In the IDA PBC, you say, I want to have more. I want the new closed loop system to have new J, new R, new H, and new G. That's the idea. Simple. Of course, it's easier said than done. Okay, this is just the objective, you know. Solving, you know, this equation, you get actually PDEs that you need to solve. They're called the matching equations, and there's a lot of stuff that you can do there. So that's one direction on its own. So in our case, when we have the robot manipulator, as I mentioned, we have the control port and the interaction port. Okay, and I'm gonna skip this slide because I mentioned it earlier. Okay, the goal when we have a robot that we want to interact is that the controlled robot should result in a passive behavior seen from the environment port. And because we have this, if we enforce this by the controller, then we have guaranteed contact stability. There's something here before I move on. I mentioned last time that actually, you know, there was this experiment I told you about, you know, where we can have two robots and one of them can emulate this behavior. I haven't found it. I digged so hard. I didn't find this experiment per se where the robot actually is interacting with another robot, but I found a lot of work actually dating back to the old times of what that Neville Hogan was very active in that area. He actually had a lot of work showing that, you know, this idea that you can have a passive controller and a passive environment, you get stable behavior, and you can have a non-passive controller with a passive environment and you show non-stable behavior. So there's actually a lot of work there. I found some stuff also in leg robotics. I tried to find the videos to put them, but I was not successful. So because some of these are like 1985 or something papers, so it's not easy to find these videos. Even though I remember after last time's lecture is that I already saw a video before, but I couldn't just try to find it. It's already, I'm sure it's on YouTube, or I saw it live from. No, actually no, it was on YouTube. And Neville Hogan was given a presentation, and he actually put this result. So he put this result where he showed when you can have a stiffness where you can show that a non-passive controller is unstable. So last time what I said that, you know, I haven't seen, so I'm just correcting what I said last time, that I haven't seen this experiment before. I did see it, and I already found some stuff in the literature. It's just not, you know, it would be great to replicate it, you know, with an actual robot to really have this have our own video. So if you're interested to work on that, let me know. Okay, so we do have a lot of, you know, stuff that we can repeat this simple experiment. Yes, ma'am.
Robots, I think there one paper they are making formation control of mobile robot where they are using the Port-Hamiltonian.
Yes, absolutely. Yeah. I'm not saying that. No, sorry. I did not mean that. I haven't seen any papers where they use the Port-Hamiltonian to connect robots. This already exists. For example, like multiple, when you have multiple mobile systems, that's for sure. What I mean is that do you have a dedicated paper or a dedicated research that shows one controller with a passive environment done by a robot? So the passive environment will be the robot now. It's acting as if it's the environment. And it shows that one passive controller is stable and another non-passive controller is unstable. That's the idea. So, but really show it with robot manipulators. I haven't found this yet. It's a very basic, fundamental research. It's not, but it really shows that this theory is actually is experimentally validated. Okay, in a dedicated paper. There are already previous stuff, but they were just in 1 dimensions and 1D impedances and with linear springs and so on. But to really show it in a SE3 manner, I haven't seen this before. Okay, so for any of you PhDs, if you're interested in something like this, this is very interesting. The standard impedance controller that I showed you earlier is actually passive. Okay, but what I'm saying is wrong now. What is wrong in what I said? When I say the controller is passive, what's wrong about this?
Supply.
Okay,
How it is not passive.
it should be the closed loop system, exactly. When you want to look at the passivity, you should look at not the controller is passive, the closed loop system is passive. By the way, our original system, okay, which is the energy, which has the gravity, actually was not 100% passive, because if you have a drone, it can keep on falling forever. If you remove the ground, it just can keep, if you have a hole in the ground, it can keep on flowing up, till forever, until it hits the core of the earth. So in the end, there's actually some people try to introduce an intermediate concept, something called cyclopassivity, if you see about it. But this is technical detail. The whole idea is that once I compensate the gravity of the robot, and I have here storage of potential energy, of kinetic energy, and I have here storage of potential energy in the spring, and here damping, everything else is passive. Okay? So the closed loop system here with the standard impedance control is passive. You can show just because of this idea that we have the Dirac structure, that this Dirac structure in the end will say that power in this port and 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 power in this port, all of them sum to 0. This is exactly what the Dirac structure does. If you write this by hand, you would spend, like half an hour just, especially with all of these technical details of the spring and so on. But in the end, it's just one equation equal to 0. And you can also rewrite it that the energy that's supplied to the controller, so this is the one that is supplied to the robot, can be written as minus H dot, which is the potential, plus Hg dot, and minus something related to the damping, and minus something related to the other end of the spring. Because if you have one spring attached to the robot, and the other one, this is the desired set point. If you keep on moving it, you're also exerting energy in the system. So you can also make some assumptions here. So in the end, you can make some assumptions on how are you moving the other end of the spring. You can just say it's very slow, such that I'm not doing active. I'm not actively moving it much faster than, for example, in the damping. If you just make some assumptions here, you can show in the end that this impedance controller plus the robot, okay, all of them, they have a stored energy, which is kinetic and potential. What about the gravity? What happened to it? It was canceled out. It was compensated by the controller, so we don't have any gravity anymore. And this is less than or equal the interaction. Okay, wrench twist to transpose with the twist. So we do have passivity of this controller with respect to the environment. What does this mean? Why is this important? Then everything in this circle, in this figure, is passive. You have, okay, you're done. You have guaranteed contact stability. Yes.
Regular one, but split the HK and HP.
Yes, exactly. Because in the closed loop system, we have multiple Hamiltonians now. And this is the idea I said, I think, last lecture and in the lecture before, which is that because you interconnect individual Port-Hamiltonian systems, the new Port-Hamiltonian system will have an energy function that corresponds to the sum of all of the previous ones. So all of this, all of this diagram is a new closed loop system. It has one Hamiltonian that corresponds to HP due to the spring, H due to the robot, but the H here was kinetic plus the gravity. And I have here minus the gravity. So minus the gravity and the gravity here, they cancel out. I'm left here with the kinetic, and I'm left here with the potential of the spring. So these two, you can recall them as the total energy of the closed loop system. So the total energy of the closed loop system is less than or equal the only open port it has, okay, which is that one. It has another one, which is this, which is coming from how you move the spring. You know, for example, if I take the spring and I tell the drone to go to this place, I'm moving it, so I'm exerting energy. But this is you produce from a trajectory generation, for example. You tell the drone go to this point and then go to here and then go to there to do this action. If you want to draw a circle, you tell it draw the circle. So you're moving this, for example, to have the behavior of a circle. So you have full control on this. You know, you can always see that really the energy is less than, you're not violating this specific. But the other side, which is the environment, I have no control about. Okay? I might be pushing with a human. Okay? The only case where you can have really, actually the human, okay? Some people did some studies and showed that a human, because he has, you know, limitations on the muscles, you cannot produce a lot of energy there. So a human can also be considered like a passive, okay, subject. Okay? You can put some limitations. I talked a lot about passivity. And we added one extra condition. We said that, what if I want now to do high performance interaction? You know, I just don't want to go to one place and to push on a wall. I also want to push with a desired force. In general, a desired range. So I want to have, you know, precise interaction. The easiest way to do it using as an extra, you know, to this controller is simply to make the stiffness of this 6D spring variable. So I add, so here we're going to be splitting. I'm going to have something with a constant spring and something with a variable spring. Okay? The variable spring, okay, will come from another potential function. Okay? But this time, this potential function is a function of h, you know, the relative pose between the two ends of the spring, but also the k. As an analogy to this, if you have a 1D spring, what is the potential function of it? Half k x squared. You all agree? What is the only thing that changes with time? X. So when I calculate the rate of change of this potential function, I should get force. I should get like kx multiplied by x dot. Everyone agrees? So this is if you have a 1D spring that has a constant stiffness. But what if you have a 1D spring that has variable stiffness? So the k changes with time. So it's no longer that you have one state, you have two states. And no longer that you have one thing that's, you know, that's a function of time, which is the x. You have also that the k is a function. Sorry, you don't have the state x is a function of time, but also the k is a function of time. So I have x dot and I have k dot. So when I'm writing the rate of change of the energy function, it should have something related to multiplied by x dot, which is the spring force multiplied by the x dot. And I have something that's related, you know, to the gradient of the function with respect to the k multiplied by the k dot. Generalize this to 6D, you get this equation. Okay? Of course, it becomes, you know, nasty and you get all of this geometric stuff, but it's exactly the same idea. You have something related to the original idea that you have a wrench due to the stiffness, and you have something related to the k dot. This k dot is what you can design an adaptive law to it. So this is exactly how we do adaptive control, for example. So now I'm going to be designing a law for the k dot. The k dot, you can simply choose it as something that will involve the desired wrench. So as long as I have an error between the desired wrench and the interaction wrench, okay, I just keep on increasing the stiffness. And if I reach there, I just make the k dot equal to 0. So I just keep these values I reached. Very simple. This is actually a very simple proportional controller on the interaction wrench. To do this behavior, where do we get the interaction wrench from? So now actually I know I'm pushing at the tip of the robot, and I need to know how much wrench I'm actually pushing with. So this is the actual interaction wrench. How do you get it in real life? Using a force and torque sensor, exactly. So you need a 6D sensor. It's actually called just a force and torque sensor. They don't call it a wrench sensor, unfortunately. They don't know what a wrench is. They just call it, if you search on Google, you just look for force/torque sensor. Sometimes they call it a 6D force sensor. What do they mean by 6D force sensor? A wrench sensor. Just 3 forces and 3 torques. The way we did it in the paper, Okay, and some people again, so this is another way of designing of using this. You can actually design what's known as a disturbance observer that can observe or try to estimate what this interaction wrench is, and then you can plug it in to the stiffness modulation module. Okay? So in the end, what you have here, these are blocks that are doing only signal processing. They don't have dynamics of their own. They're just signal processors. One of them is trying to estimate what the interaction wrench is. The other one is changing the stiffness. And afterwards, you have something that supplies energy to the variable spring. Now, without doing all of the energy analysis that we did before, eyeball this figure. Do you see it's passive or not? Is it passive or not? So the variable impedance controller, is it passive? Why?
The environment now is not passive.
No, forget about the environment. Let's leave this one open. Is this closed loop system, including also all of these parts, compared to this open port, is it passive or not? Why? This one? This one? So the power here. Can you guarantee that the power here is always decreasing? Can you always guarantee that K dot, how it will change, is always decreasing? In general, not. K dot can increase or decrease. So this can be positive or negative. So this means that this port, the power through this port is indefinite. I cannot say whether it's always increasing or always decreasing. So this means that this behavior, this signal processor, so it's a signal processor, from an energetic perspective, I cannot guarantee its passivity. Thus, I have one component in all of this part that's non-passive, which means that the overload system is non-passive. Try to do this by paper. You would spend, I think 1 hour. If you had this controller and you just, keep on canceling this with this, this with this, this with that, and in the end, you're just left with some part K dot multiplied or, paired with the gradient of H with some K, and you conclude that I do not know whether this term is always positive or always negative. But here with bond graphs and with the Port-Hamiltonian system, the rock structures, I don't care about them. They are, they don't produce or dissipate energy or store energy. They're out of the region. All of the nonlinearities that were inside, they're just gone from the energy analysis. So I have a direct structure here, which is for the controller, direct structure here for the environment, and there was a direct structure inside of the robot. All of these, I don't care. The gravity compensated robot, we said it's passive. The impedance controller, all of these parts are passive. The only thing that was new is the variable spring, and this is the only open port. I cannot guarantee it's passive. Without even writing one equation with this figure, I can immediately see non-passive. Question?
Okay, so talking about guaranteeing the sign of the K dot at that particular point in time.
Guaranteeing the sign of this term. The K dot paired with its term that will appear in the energy balance.
But then what is actually changing as the K dot?
The K dot. It's known. You can write it, yes.
K dot now. The whole point is we have the set putting the wrench that
With this one, the desired wrench, yes.
then we have whatever it is we're interacting with, we want it such that it reaches that point and
Yeah.
the K dot cancels out.
That's right.
In this case scenario, in what case scenario would we have something negative?
Is K dot always positive or always negative or both? So if this minus, if this one is bigger than that term, you have minus. Sorry, you have positive. If this one is smaller than this one, you have negative. Can you guarantee the sign of K dot?
Starting from zero interaction.
Yeah.
Wouldn't it be the case that as soon as it gets to that particular point, it disconnects and we
What if you want it back to zero? So I want to have positive force. So I want to push and then pull. Push and then pull. It's indefinite. So this term K dot can be positive or negative. This term is indefinite. I cannot say whether it's always, I cannot guarantee it's always decreasing. Okay. So that's the conclusion. So this is a non-passive controller, sorry, non-passive overall system. And this brings us to energy aware controller. There's some stuff here on energy aware control. I have to skip it just for the time purpose, and so you can read it at home. And I'm just gonna tell you about what should change now, okay, to have this energy aware impedance controller. Okay. So the part I skipped here is just about the general philosophy. Just like when we had the general philosophy about passivity-based control, there is a general way of looking at designing what's known as energy aware control. You can look at it at your own pace. But one way of restoring the passivity that we violated because that we regulated the interaction range is by using what's known as energy rounding and energy tanks. This is something you're going to only find, okay, exclusively in the Port-Hamiltonian literature, or in ways or people that do stuff like Port-Hamiltonian, but they're not just calling it. Okay, one of the most famous people I know in his group, or so for example, Sami Haddadin. So he's one of the founders of Franka Robotics, or the Franka Panda and all of these robots. So he's doing a lot of stuff, with energy tanks. He's very active on this. All of the commercial, a lot of the commercial robots that come from Franka, they already have these energy tanks implemented in it. But from a conceptual point of view, it comes exclusively from the Port-Hamiltonian literature. Okay, so the Port-Hamiltonian people, one of them was my supervisor, stiffness. So he's actually the one that invented these energy tanks. From where? From thinking about this port-based thinking. So this port-based way of thinking. On the other side of the world, and so in the US, so Neville Hogan in the 80s, he was also the first one to think about impedance control. It's widely used now. So any robotics class, any robotics graduate should know about impedance control. And back then, he introduced it for the first time, and he was also thinking in terms of ports and in terms of bond graphs at the same, okay, in this way. So the basic idea behind energy rounding is that now looking at all of the energy that now, because I see the energy in the system, so because I know that there is energy flowing, the controller is no longer just an equation inside of a computer. It's actually emulating some physics, and it has some dynamics of its own, and it has some energy of its own. You can always route, you can always take some excess energy that exists in the system. For example, like the damper. You have a damper that dissipates the energy. So I can take this energy and put it back into a tank. I can put it into a storage element that people call an energy tank. And now when I'm doing a new energy analysis, and I take this energy that was dissipated earlier, but I stored it now, I can compensate for any energy that was lost due to passivity. This is the bottom line. Okay? Very simple. So in a cartoonic version, exactly what energy tanks will do the following. We have the interaction range controller, okay? And we get from it this regulation range, so the range that I use for tracking or for regulation. And this action, it required some energy. Changing the K dot, which is in the end this regulation range, changed the energy balance. Okay, it's indefinite. But I can always provide the power it needs from an energy tank. And this energy tank, I can initialize it with some energy budget. So I can put some energy, and I can say, okay, if you use all of the energy inside of this tank, stop the wrench regulation. Because I calculated or I estimated from the beginning that I want to do the task, for example, like to draw a circle. And I made some assumptions on the environment, and I said, in the end, I require 1 joule of energy. The environment took 5 joules. This means there's something wrong, either in my estimation or in the interaction itself. Something happened that I did not take into account. So the energy tank, I save some energy into it, or you can also take the virtual damper that we had. We can take this energy, we can dissipate part of it, and we can take some part of it into the energy tank. Okay? This is a very weird way of doing control. I'm pretty sure you didn't even know that you can do control by thinking like this. Okay, but it's possible. You can write a controller like this. Everything else, is just math, okay? A lot of details, but this is just the bottom line of what this controller does. It's very intuitive. The math, is just gonna get involved. I don't want to spend the next hour, okay, just talking about the math of this simple idea. Okay? Yes. You will ask about the math, right? Okay. Sorry.
Initialized energy.
The initialized energy, yeah. Sorry? Number. For the controller, you can think of it as a gain. I put in the controller, and I try to say that if you use this energy, stop the interaction. That's it. I'll show you a video that will make this clear.
I think it look like not, but gain scheduling, like we know the tank, we have all the numbers, and on the basis of the stiffness, we selected the desired energy for that.
On top of what I just said, you can do gain scheduling, that you can say that if I'm doing this task, this is your energy budget. Doing this task, using the energy budget. But gain scheduling is different. You think about it, you say that the PD controller have these gains if I have this task, and these gains if this task. You can also do this, by the way. You can gain scheduling as a concept is easily added here. You can have for one task, one impedance, one task, one impedance. For example, if you're cutting, a cucumber, you're using some impedance parameters that you trained, that you learned before. But you know that a cook uses very quickly. He cuts the cucumber because he already trained on it. So he has some initial guess about what is the impedance behavior I should have. If a pizza maker is trying to do pizza and trying to expand, make a very large circular dough, then he already was trained on I should have this at this I should be very stiff initially, I should be very soft in the end, and so on. You can program all of these impedances, all of these behaviors using gain scheduling. Yes, of course. Yes, I think. You got another question? Yes.
Here we say virtual damper, but in the system we say it's neither create or not only dissipate, but how we will store that virtual damper energy in the tank, like.
So we said that a passive system can either dissipate or store. So the damper was dissipating energy, and the stiffness, that's the virtual spring that we added in the impedance controller, was storing energy. And now we're going to have another way we're going to be storing energy, which is the energy tank. So this is another place we're going to be storing energy.
We are just adding new energy tanks.
Exactly. You can add as much as you want from it. Exactly. So as a concept, doesn't matter. Of course, the behavior, different system. You need to think about what's the energy here and energy there. But in principle, you can add as much as you want. It's your control. Yes. Question?
Regarding so if we want to initialize the energy tank, we should have some knowledge about that.
Absolutely. And this is so that's the catch. You should. So everything I'm going to be showing you later depends on what the number that you put in the energy tank. And this is the open research. So this is what a lot of people are working as research now. That's why I'm interacting with an environment I don't know the model of. I don't know if I push on the environment how it will react back. But I have a guess that this whole process, you can do it, for example, in a training fashion. I take the robot and I put it in the environment, in a closed environment, and I say that, train to do this task. And I'm gonna, because it does it 10 times, I take the average of all of these times. I know exactly how much power requirement it needs for this specific task. Next time, when I take this, when I take this robot and I put it in the real world, I know that it requires 1 joule. Because I did simulations, for example. You can get this number from simulation. You just need to have an estimate. That's the idea.
Somehow this implies still passivity. For example, we're saying K dot, we're increasing, we're decreasing, which made the problem.
Yes.
If we have the energy of whatever 5 joule or so, we will keep increasing or decreasing, we still according to the error. So how the energy tank implies the passivity, while also we change K and sometimes positive, sometimes negative, depending on the error, right?
Because we put a lower bound on the energy. Or in other words, a higher bound on the total energy that can be in the system. If you exceeded this energy, because this is the number that we put in the energy tank, then you stop. And this is why this is related to the integral way of talking about passivity and the differential one. The integral one, you need to have that the energy you started with is less than what you ended with. So you're thinking in terms of the energy. The differential case, you're thinking about the power, and this is a little bit limiting. That the power is always less than or equal to 0. But this is not the definition of passivity. It's equivalent, but not the same.
Around to not blow up.
Exactly. You're putting a boundary so that you don't blow up. That's exactly the bottom line. I saw more hand, yes.
What's the limit? Initializing the energy. What's the limit of say, for example, something very high?
Absolutely, excellent question. So why don't I say that I have 1,000,000 joules? Is it passive? Theoretically, yes. Is it safe? No. No. Even with the physical limitation. Let's say that I give you a very strong robot, and it wants to move from one place to the other. Okay, and you're a human in there. Would you be safe to be with a robot that goes at a speed of 100 meters per second? I don't know if that's possible or not, but just a number from out of the top of my head. 100 meters per second, and it has, it's a big robot. It might kill you, right? A lot of people are working on this. Actually, the group even of Sami Haddadi. Actually, Sami Haddadi's work himself was actually in his PhD was on safety. He's very famous for safety, working on robotics. Okay? So using robots to make them safe. And this is, I think, something I mentioned earlier, that on paper, passivity and stability, these are stuff on paper. In real life, you need safety. You need that when I have a robot and he's opening a valve or trying to insert a key. You don't want the key to break. You don't want the keyhole to be damaged. If you're capturing a fruit from a tree, you don't want the fruit to be, you don't want to get it juice, you want to get it as a fruit. So there is safety there. So completely different way of thinking. Energy tanks give you the tools of how you can solve the problem. It doesn't, it's not like, it's a rule book where you say it's done. The problem is done. It's only the starting point of, if you have this problem and you think of in terms of energy tank, you need to think of all of this extra stuff about gain scheduling. What about the initial energy? Where do I get it from? And this is open for research. So this stuff is very new, very open for research, and a lot of people are working on it right now. But as a framework, it's very powerful. It gives you the tools to do a lot of stuff that you couldn't do before. You cannot do it with passivity. Passivity is very limiting in that. You cannot do it with just standard passivity because the stability, because you need to know about the environment. You cannot model it, and so on and so forth. Okay. Yes. Yes. That's in practice. In theory, any number would work, even 1,000,000. It's still passive.
But the lowest amount of energy and to provide that our system is passive, or we want more energy.
That's the thing. Depends on the objective. Stability means I don't blow up. Passivity means that the same, right? It implies that energy is just decreasing, but I can have very high energy, right? And I can still be non-increasing. This is why you need extra stuff, which is safety. It's a different concept. You need to look at the real world now. Am I talking about a robot interacting in the same environment with a human? Then, of course, the most important thing now is that the robot doesn't kill the human. So you need to look at, for example, a lot of people are working on this, that how much forces or how much energy can a human take before he gets his brain, But I can still get hit by a robot. I might not die, but I might get mental issue. So if I get hit a lot and again with the robot, I might get issues after many years. So there's a lot of stuff from the medical side. You need to understand you need to put numbers. You need to say that, and there are standards for that. So people working in standards and in this area, they say that if you have a robot that you want to get certified, and it's working, you want to call it a cobot. Have you heard the word cobot before? Collaborative robot. A collaborative robot, because it's gonna be working in an environment with a human. It needs to have certain criteria. This is one of them. That, for example, it cannot hit a human, it cannot damage the human, it cannot kill a human, and all of that stuff. So you need to put this in numbers. And energy tanks is one of the way that you can transform all this into numbers, and you can take all of these numbers and put them in the controller. You can enforce some control behavior. Yes. Efficiency of? Yep. All of these are extra requirements. Excellent question. All of these are extra stuff. Now we have the basic concept. You can always add more stuff. There is one thing here that is the way that you can add as much as you want of the concept. The sky is the limit. There's really a lot of stuff that you can add in here. And this is something called valves. You see, all of these are just paths where energy can flow. And you can always, start and stop some parts. Or you can say that I want some energy to go here and some energy to go there. What does this remind you of? No, what does this remind you of? What's this behavior that, you have something that's flowing and it goes from somewhere and goes to other places and so on? Pipes, exactly, pipes. It's hydraulic systems or pneumatic systems. Just, you have energy here is similar to water flowing. High energy, low energy, and you have valves in between. The valves are what you use for control. You can select that I want few energy to go here, more energy to go there, and so on. So valves here, so you can do valve-based energy tanks, and you can call it whatever you want. A lot of people are working on this, okay, and trying to extend energy tanks with valves depending on the task. So the whole idea is that the principal idea of energy tanks is this. Okay? You need to make it more, and you need to tweak it for your problem using more valves, and you can make it bigger and bigger. Virtual valves. Yeah.
This is like for example, if we have really high energy in the tank, to supply at one of a time, or like the continuous flow to be small energy, not to blow up or not to get too high for energy, right?
Yep.
Okay, so we have too much energy to guarantee stability and passivity
Exactly.
in theory, and we have safety via, for example.
Absolutely. That's the whole idea.
Variable such that
It is variable. Absolutely. That's exactly how it is. So the controller now, so this is how the energy aware impedance controller compared to the previous one looks like. So the regular impedance controller was, I had a spring, it was with a constant stiffness, and I had the gravity compensation, I had a damper. Now I have an extra term that corresponds to the variable spring that I was tweaking, and I have some alpha multiplied by. This is the variable that's regulated by the energy tank. If alpha is 1, what are you saying? What are you saying? Do the regulation. Do the wrench regulation. If you say alpha is 0, close the wrench regulation. And of course, you can make this transition very smooth. You can make it with a sine. It doesn't have to be like sudden. It can be very smooth. You have full control on it. But the question is, when should alpha be 0? So the whole idea now, the controller is simply, you can think that now I have a variable spring, and alpha is simply the valve, how much the valve should be open. So alpha of 1 means the valve is fully opened and allow all of the energy that's required for the stiffness changing, for the modulation of the stiffness. It comes from some energy tank. What about the tank itself? After some time, you calculate that the energy will decrease and decrease and decrease and decrease. Depending on how much energy you put in this tank, you can finish the task safely or not. Okay? So if something wrong happens, and this is the whole idea, if something wrong happens, for example, the tank was depleted very quickly than you expected, or suddenly, you just lost, this means that the power was used for something else, not for the wrench regulation. Or if you have spikes in the water, all of these spikes can be related to the energy dot. So the energy dot, which is the power that's flowing here in this valve, this can be something like the pressure. You can also sense the pressure. High pressure in a pipe. What does this mean? Signal. Something is wrong. High pressure means, okay, there's something wrong. What do you need to do now? Turn off very quickly for safety reasons. Exactly the same, concept that you think. Okay, the intuition that you have from dealing with normal pipes, and you can do it in control with a little bit of math that you need to read if you're interested. You can write everything in one graphs. You can even have more. Now you can think in terms, because you're thinking in terms of energy. You can think about, what if I have a situation where I thought something is wrong, but I don't want to turn off. I need to make extra analysis. I need to really check whether this is true or not. You can have something like energy freezing. You can freeze the energy in the tank. You can go check what's going on. If everything is safe, don't stop the regulation. Come back and unfreeze the energy. You can do all of the crazy stuff. All of this is open. All of this is a lot of stuff that you can do. I want to end up with the video. This is the same video I showed you last time, but I want to emphasize here what you see on this third plot. What you see here in the third plot is something that's decreasing and decreasing and decreasing. What do you think this is? This is the energy in the tank, exactly. So I know that I want to interact, for like 90 seconds. After the 90 seconds, so I put this energy, for example, it was like 1.7 joules. And after it depleted, see what this red curve is? What is this red line, dashed line in the third plot? This is the alpha. This is the alpha. For all of this time, it was 1. After this point, what happens? It became 0 because the energy in the tank, it just depleted. And I told the wrench regulation stop. So you see here in the beginning, you see, and in this plot, in the first plot up on the top, in the all from 0 till till I think it was about 90 seconds, the wrench was always at the one that was desired. But after the tank was depleted, it just turned off the wrench regulation. It's still pushing with a force. Where does this force come from? Can you guess? From the constant spring. Exactly, excellent. From the constant spring, I still have a constant spring and a variable one. So the constant one is producing like 3 newtons of force, and the variable one is the one that follows, what I want it to be. Yeah. The next video is that you can do exactly the same while the drone is pushing and having a pose on its own. Okay. So in this video, we're controlling both the position, for both the interaction wrench and also the pose of the robot, the orientation of the robot. Okay. So I'm regulating a wrench, I think about 5 newtons here. It's pushing with 5 newtons, which is 0.5 kilograms. That's a lot of force, by the way, 0.5 kilograms. And the drone is just tilting, and at some point you see the energy was decreasing. For this experiment, we did not make the energy to be 1.7 inside of the tank. We made it like 17. Okay? So because if we made it 1.7, it will be depleted very quickly. So that's the idea. You just put different energies in the tank depending on the task. The last one, which is what happens when you use a standard variable impedance controller, the one that only regulates the wrench. Okay? Doesn't have all of these energy tanks and all of this stuff. I showed you this video last time. So you're regulating the wrench, and at this instance here, we're going to be removing the environment on purpose. The robot doesn't know that the environment was moved, so it just keeps on increasing the stiffness until it reaches the state where it cannot handle it anymore. Okay? It becomes unstable. And the last experiment is we're going to be doing the energy tanks. So now the energy tank is running, and be aware, okay? The controller does not see, so the robot does not see the environment. In this experiment, we're not seeing the environment. It only senses, it's just sensing. It's like pushing on a wall and closing your eyes. If the wall is not there, what do? You don't push forever. What do? You feel immediately without seeing that the environment is not there. You just say that, okay, I should stop pushing now. That's exactly what the robot will do. Yes, but even before, the sensor was reading the feedback. It was reading that the robot, that the environment is not there. Okay, but yet it kept on increasing it. What we want to do here is that once the environment is lost, you want to stop the regulation. This is what you want to tell the controller. And that's not what I wanted to show you. And so now it's pushing. There is energy in the tank. Okay, and everything is going as normal. They're just decreasing. The alpha is 1, and suddenly the environment itself will change, and the robot will peacefully turn off the wrench regulation.
Don't we decide the alpha?
The alpha, no, the alpha is calculated based on it has a law of its own. So the alpha, it has some sort of like condition. You check whether the energy in the tank is bigger than the threshold, then you keep the alpha on. If alpha is less than a threshold, you just turn it off smooth. So it's not something that you play around it. It has a law that it governs how it should be. Yes?
And it observes that it's going less than if at threshold and it stops.
No, here we do it with the spike, sorry. We look at that, there was a spike in the energy going out of the tank. So there's something wrong, We have a threshold on the spike, on the power. If it's bigger than the threshold, there's something wrong. And of course, you might think of the question, what if the the environment was gone, and it was gone very slowly, you know, not immediately. So you can still have the same problem. But what I guess is that because of the energy that you have in the tank, if it was already calculated properly, it will deplete very quickly, and you will not have the same situation that you had earlier. But this needs to be shown. We haven't shown it in this world. Sorry, Pauline.
Not only to change from 1 to 0, maybe.
It is already like this. It's already like this. Because if you make it sudden, you're going to have shattering inside of the controller. And this is very bad. So usually we do have, you know, a very smooth transition from alpha being 1 to alpha being 0. You can actually see it here. It's actually there's this smooth. Okay, depletion. Yes.
If the reverse was happening.
Yeah.
He pushed
Exactly. Yeah.
the environment. The same will happen, or the passivity will be.
Excellent question. If you push on the environment, what will happen is that the desired frame is here, for example. The actual frame becomes back. What happens to the force? It should decrease. Because if you take a spring and you elongate it more, what happens to the force? It becomes higher. So the actual force that the robot is applying to the environment becomes higher. And you had the desired one in mind. So what happens to the controller? What happens to the variable stiffness? What should it do? It should be softer. The variable stiffness spring should be softer, such that the total force that you're applying in the end is the one that you have then desired. We did not show it experimentally, but it is exactly.
Thinking like how the environment is generating energy. We're saying a robot arm that's fixed or
Yeah.
no, now if we move the environment, isn't it the same as giving energy?
That's right. Absolutely. Yeah, you are. But that's the thing. So we can still work with environments that are active, you know, provided that this energy tanks gives us a way in general. So on paper, and this was one of the misconceptions a lot of people have. Energy tanks on paper, they actually allow you to do any controller. You can make it from being non-passive to being passive with this trick that you can add as much energy as you want and everything on paper is working. So from a conceptual point of view, it's a way to pacifize any controller. So which means that passivity is no longer, you know, a check, you know, because if I can always do this trick, okay, I can add as infinite amount of energy as much as you want. It's still, you know, bounded. Everything from a mathematical point of view is safe and you're good. But the true value of what the energy tank is that it gives you a way to estimate. If you go back to this bond graph, what the true reason of what the energy tank is, especially all of the power going inside of it, this power is related to the power flowing through the environment. And this is very powerful. You have a way that you can estimate from inside of the controller what is the power supplied by the environment. Because everything else is stored or dissipated, so you exactly know how much they are. So this is completely model-based, of course. We're not doing any model-free stuff. I have full knowledge about the system. I have full knowledge about all of the stuff. If I have uncertainty, if you want to do this in a robust way, just add, you know, some you know, upper bounds, you know, upper and lower bounds. You can do everything. I have an estimate. It's either I'm between this range and that range. You can ever do everything like robustness. Actually, I haven't seen this being done in a robust way, but this is one nice way that you can extend this. Right? Again, open for research.
Wait, another point. Why we keep the constant spring in the graph?
Very good point. Because this is only just, you know, for technical reasons. If you only have the variable spring and you allow the stiffness to vary as it wants, you know, from the adaptive law, in principle, it can go to 0. And stiffness being 0, what does that mean? You don't have a spring in the first place. So you're not going to be going to, you know, to the desired place. So you lost the position control. You turned off the position control. You don't want that. You want to have the position controller or the post controller, the initial one that you had. You know, I have a controller that's tuned for free flight, and I can use it for interaction. But afterwards, once I'm interacting, I turn on the wrench regulation, and it will add the extra wrench that I want using the variable stiffness. Yes.
to regulate my force.
Yes,
But for the variable, I want to regulate the range.
absolutely.
So, because I had this question, if this constant was, if I keep on changing its value,
Yep.
so at some point it can be unstable, but this is not the case because it will be unstable or not passive if just I'm doing branch regulation. So this variable stiffness is not the same. It's not the same as constant stiffness because their motivations are different.
The use is different, but whatever can happen here can happen there. So even if the wrench, even if the stiffness goes beyond some limit, I can still have dynamic instability. You know, you can start, because we assume everything here is rigid. For example, if you have a drone and you start to ask, you start to make the stiffness very high, you start to excite the high frequency, all of the high frequency dynamics that we completely forgot about. You remember the first lecture, we said that all of the dynamics of the motors, all of the aerodynamics were just, not there. The robot is very rigid. I don't have any stiffness inside. It's not true in real life. I always have stiffness. I have carbon fiber. I have very lightweight material. So it has all of these high frequency dynamics that were just, not making mad, not making angry. But if you have high frequency behavior in the controller, you will excite these high frequency dynamics, and this will make dynamic instability in the frequency domain. Even in both, either one. Yes, you can have that. So I'll stop now because we're way over time. So I hope you enjoyed the 3 lectures. I tried to make them as general as possible without all of the nasty details. If you like the nasty details, they are in the paper. So if you ever go through them and you want to have any questions, please feel free to come. Thank you very much for coming. So this presentation wouldn't have been possible without, your motivation and being here. So I really appreciate your motivation and you're willing to know stuff. There's no attendance, no quizzes, no grades, so you're free. So جزاكم الله خير. السلام عليكم ورحمة الله وبركاته.